welcome to Genique. Today I am here to teach you the subject Electromagnetic Theory, and this subject plays very important role in the GATE and as well as engineering services examinations and also some other public sector unit examinations. Okay, so it has a good weightage in the GATE examinations and engineering services examination and some other examinations also. See, one should concentrate on this subject. Okay, for the GATE point of view, you will be having 8 marks to 10 marks. It is for ECE people. Okay, but for the electrical people, the weightage will be around 4 marks. Okay, so now the full course of this electromagnetic theory will take around 60 to 65 hours of class. Okay, but for the electrical people, you will be having maximum 20-25 hours. See, when compared to the ECE people, the electrical people will be having a less weightage because the syllabus will be very less, but the revenue is good because for the electrical people it will be 60 to 65 hours of class. So if the people concentrate 60 to 65 hours of class, they will get 8 to 10 marks. But the electrical people, if concentrate on this subject for 20 to 25 hours of full class, they will get 4 marks. So when compared to these people are having a good weightage. So, and it is very easy for you to score these marks. Okay. In general, the total subject is divided into the 5 chapters here. The first chapter is electromagnetic fields. It is static and time varying. Okay, the first chapter is electromagnetic fields. Okay, static and time varying fields. So the second one is the uniform plane waves. And the third chapter is the transmission lines and the fourth chapter waveguides and the fifth chapter antennas and the basics of radars. Okay, for electrical people, you will be having only this chapter. So this is for electrical only. Okay, so here the first chapter includes the electrostatics and also the magnetostatics. Electrostatics and magnetostatics. Here in the first chapter we will study simultaneously the electrostatics and the magnetostatics, and we will not study this chapter by chapter. Okay, so for better understanding of the subject, we will be studying the electrostatics and the magnetostatics here. Okay, it is for the static and time varying fields. And the second chapter is uniform plane waves and the transmission lines, waveguides and the basics of antennas and the radars. Okay, and some portion of the fiber optic communication is also added in this subject for ECE people. Okay, so now see, for the first chapter, you will be having a good weightage from these 4 chapters, okay, in the GATE examinations. So you will be having a good weightage from these 4 chapters for the gate examinations. Okay, but it will play very important role. It will play very important role in the engineering services examination, the first chapter. So the first chapter is having a good weightage in engineering sector examinations. Okay, so one should concentrate on the first chapter very clearly. Okay, so now see, in this crash course we will be dealing with 14 to 15 hours of class. So in this we will discuss only the topics, very important topics where the students can feel difficulty in solving the problems. Okay, so we will choose those topics only and we will discuss, and remaining topics can be cleared by you only. Okay, so here we will discuss only some of the complicated topics, and before going to that, and we will know what is the subject clearly. So what is the name? Electromagnetic theory. Okay, so electromagnetic theory is the subject with the study of both the electric fields and magnetic fields, and the study of both electric and magnetic fields. Okay, it's the study of electric fields, magnetic field, and both the combination of electric and electromagnetic fields. Okay, so this is the electromagnetic theory. See now, so how these electric and magnetic fields are generated. Okay, so there must be something which is causing these fields. Okay, which is causing these fields. So you must be having some cause to produce these kind of fields. In our childhood means 8th, 9th, 10th standard and 11th and 12th standards, and we will be studying, we already studied that how the electric field is generated. How the electric field is generated? Suppose if you take any point charge here, if you take any point charge here, a positive charge, okay, we observed that the electric flux lines are coming out of this point charge. So these are called as electric flux lines. We studied these things in our 8th, 9th and 10th standards. So how we will get these electric flux lines? How we will get these electric flux lines? So already we studied that what? These electric flux lines are straight lines. Okay, these electric flux lines are straight lines. So how we get these kind of straight lines here? So see, if you take a point charge in the space, okay, if you bring one more test charge to this, near to this charge, automatically if you take the positive point charge here, if you take one more positive test charge here, so automatically there will be a repulsion. So it will be repelled in this direction. Okay, so like this, suppose if there is a charge, if you bring one more test charge plus Q here, and automatically it will be repelled. If you bring one more test charge here, it will be repelled. If you bring one more test charge here, it will be repelled. It will be repelled. So like this, the repulsive forces, okay, the lines containing the repulsive forces are called as these electric flux lines. Okay, it is the force direction. It is the force direction. So that means what's happening here? So due to this point charge Q, so we are getting the force outward from the charge. So that means If you bring one test charge here, what's happening? It is repelled from this point charge. If you bring opposite kind of charge, what happens? If you bring what opposite kind of charge, what happens? Suppose if you take a negative Q here, if you take a negative Q here, then the electric flux lines will be like this. Why? If you bring one more test charge plus Q here, automatically there will be attraction between these two, so it will be attracted towards this point charge. Okay, like this. Okay, so this is the orientation of the electric field lines. Okay, so see, observe this, these all are having the straight lines only. So if you clearly observe this is the point positive charge. Okay, it is generating the electric flux lines. So that means it is generating the electric field. It is generating the electric field. Suppose if you take a point charge around this, you will be having the flux lines like this. Okay, so you can assume a sphere around that. Okay, so that means if you combine all the envelopes of this, so you can assume a sphere like this. Okay, so it will be having the equal strength in all directions. Okay, see, if you observe this is a negative Q charge. Observe this, see, it is a positive Q. So because of this is a positive, it is repelled. So the electric flux lines are coming out of this positive charge, and if you come here, the electric flux lines coming into the positive charge. So that means this is a source E flux lines. What is this? This positive charge is source of the electric flux lines. What is this? All the flux lines are coming into the charge. So this is called as, it is the sink of E flux lines. So all the flux lines are sinking into this negative charge. So this is, already we have studied about this. So that means the electrical flux lines are radially outward from the charge. Okay, it is radially outward from the charge. Okay, or radially inward from the charge. Now, so that's why we call these electric flux lines are the straight lines. Okay, we know how these straight lines obtained. Okay, so how the magnetic field is generated. Okay, how the magnetic field is generated. So there is also a cause. What is that cause? It is a moving charge. Moving charge is nothing but what? It's a current. Okay, if you take a current carrying wire, I carrying wire. Okay, if you put a magnetic needle here, what happens? If you put a magnetic needle here like this, I am representing the magnetic needle like this. Okay, what happens? It will be deflected. Okay, there will be some deflection in this, like this. So if you combine all these points, you will get the magnetic flux lines like this. See, if you observe, see, if there is a current carrying wire, if you put one magnetic needle here, so it is having some effect. So that means the current carrying wire is affecting on this magnetic needle. So that means we can assume that there is some field. That field is called as the magnetic field. Because here this charge, this electric charge is affecting this electric charge. Okay, this electric charge is affecting this electric charge. So this is exerting some force on it. Here also this moving electric charge, thus this moving electric charge is exerting on the magnetic needle, okay, or magnet, okay, it is affecting the magnet. That means around this we can assume that there is some kind of the magnetic field, okay. And more clearly, and after having some research on it, and one person came here and he put one more stationary charge here, okay, one more stationary charge near to this place, okay, one more stationary charge near to this place, and there is no any effect on this charge. If you put one more stationary charge here also, there is no effect on this charge, and he put one more moving charge here, one more moving charge. If you put one more moving charge here, that person who researched all these things, okay, he got the same effect as of this, okay. So that means what's happening, this moving charge is rotating like this. Let us suppose this is the moving charge. If you place this moving charge near to this, and it is changing its direction and coming like this, so it is making a circle. So now we can say that the magnetic needle is made up of a moving charge, okay. Now from now onwards we won't talk about the magnetic needles here, we talk about the moving charge, okay. So suppose if you put a moving charge near to this moving charge current carrying wire, automatically its direction, its velocity will be, the direction of that velocity will be changed, okay. So these lines are called as the magnetic flux lines, okay. These lines are called as the magnetic flux lines. See, if you take a point stationary charge, we are getting the electric fields. If you take the negative charge, we are getting the electric fields. If you take the current carrying wire, moving charge, we are getting the magnetic fields. Here the magnetic flux lines are circles. Here the magnetic flux lines are circles. So these things we know in our previous classes, okay, in our childhood classes, okay. So from now onwards we should know that the electric flux lines are straight lines, the magnetic flux lines are circles, okay. See, so that means what's happening here? Here we are getting the electric field, here we are getting the magnetic field. So we can say that what is an electric field? The electric field is nothing but it is an energy format . It is an energy format that is all around the charge and influences other charge, other stationary charge. Okay, so this is an energy format. Then what about the H field, magnetic field? So H field it is also an energy format that influence other moving charge. So this is what is an E field and what is an H field. Okay, so the cause of E field is the stationary electric charge. The cause of the H field is the stationary current. Okay, so what is meant by this stationary? The stationary is nothing but independent of time. It is also called as static. It is a static charge. So here first of all we will discuss the static electric fields and static magnetic field simultaneously. Okay. Now see, so we observed that what if we take a point stationary charge, it is a point charge which is stationary, okay. So what we are getting, so because of this we are getting the electric field. Okay, so because of this point stationary charge we are getting the electric field. Okay, suppose if we take the same charge which is moving, that is the second case, moving with constant velocity. Okay, if the charge q is moving with a constant velocity, what happens? That means the q is linearly varying with time. Constant velocity means it is linearly varying with time. Suppose if the charge is moving linearly with time, then what happens? Then dq by dt will be equals to a constant. Because what? Because q is equals to some proportionality constant k. So from this we can write that dq by dt is equals to k. Okay. So dq by dt, we know that what? It is a rate of change of charge. It is nothing but the current. Rate of change of charge is nothing but the current. And this current is constant. Okay. And this current is constant. We can say that it is a DC current. Okay. So if we take the moving charge which is traveling with the constant velocity, then already we observed what? Here we will get the H field, right? And how the electric field is generated? The electric field is generated like this. If we take the point charge here plus q, then the electric flux lines are like this. Okay, see here we have taken the point charge as the static. Static means independent of time. Here also we will get the field independent of time. If the cause is independent of time and the effect is also independent of time. So due to this cause, what we are getting? Due to this point charge as the cause, we are getting this one as the effect. What is this effect? This effect is electric flux or electric field. Okay, now come to this. So this is static. Static means independent of time. Now, if you observe this, this is the charge moving with the constant velocity. Okay, so constant velocity means this current is independent of time. So that means it is a static. So if it is static means, so this is a static. So what is this is the cause. This cause is static and the effect is also will be static. So here we will get the magnetic field like this. Suppose if you take the current carrying wire like this, we know that the magnetic field will be around this. The magnetic field will be around this. And we will see the direction next. Okay, suppose if I assume the current carrying wire like this, I carrying wire like this, I am showing on the top view. Okay, so the magnetic field will be like this. Okay, so this is the effect because of this cause. Now suppose if this same amount of charge Q is moving without constant velocity, what happens? See, observe this thing. See, just we are trying to learn how the electric field is generated, how the magnetic field is generated, okay, and how the electromagnetic fields are generated. Okay, we have taken a point stationary charge. Okay, stationary means independent of time. This one as the cause, we are getting this one as the effect. Okay, if you take this one as the cause, what is this? It's the charge moving with a constant velocity. We are getting constant velocity means DC current as the cause. Okay, we are getting the H field around this. It is also independent of time. Now observe these two things. Okay, it is static. What is this point charge? The point charge is nothing but a number of charge carriers accumulated at a point. Okay, the number of charge carriers accumulated at a point. So point charge means what? It is an accumulation charge. Okay, it is an accumulation of charge. Come to this. What's happening here? This charge is moving with the velocity. That means that there is a flow in the charge. So that means it's a flow. It's nothing but what? It is a flow, constant flow. Okay, because of this constant flow, we are getting the magnetic field. Because of this accumulation of charge, we are getting the electric field. This accumulation of charge is nothing but it is a DC voltage. Accumulation of charge. The charge can be stored in the form of DC, right? See, this is a DC voltage. Okay, so this is what it can be called. Already we know this is a DC current. Okay, so because of the DC voltage we are getting the electric field. Because of the DC current we are getting the magnetic field. Now see, observe this. The third case, the charge is moving with the constant velocity. If the charge is moving with the constant velocity means what we can say? Sorry, the charge is moving without a constant velocity means there is an increase in the speed and there is a decrement in the speed. Increment in the speed and there is a decrement in the speed. So because of the increment in the speed, what happens? The charge carriers will move fast, and because of the decrease in the speed, what happens? Automatically the charge will get accumulated on the conductor. Right? Suppose if you take an example, suppose 100 people are running on the road. Okay, if they are all are moving with the constant velocity, there is no problem there. Okay, if some of them reduce their speed, automatically there will be an accumulation of the people. Okay, so there will be, if the charge is similarly, if the charge is moving without a constant velocity means there will be an increase in the speed and there will be the decrease in the speed. So because of the increase in the speed, what happens? The flow exists, the flow is sustained, and because of the decrement in the speed, what happens? There will be an accumulation. So here you will get what? Both accumulation and flow. Both will exist. So already we know, and this accumulation and flow will be depending on the time. Okay, so they are moving without a constant velocity means the speed is varying with respect to time. Okay, so that means what we can say? That means the dq by dt is equals to the constant. Okay, so what is dq by dt? it is not equals to constant. What is dq by dt? This dq by dt is nothing but the current only. Okay, this is called as the AC current. This AC current is not equals to constant. Okay, this is called as dq by dt. Already it is not equals to constant means what? It is an AC current. Okay, so because of this accumulation, we know that what? There exists the electric field, and because of the flow, there exists the magnetic field. Okay, but observe this. This is the cause. So because of cause, we are getting this effect, but this cause is independent. Cause is dependent on time. So the moment of this charge, the rate of change of this charge is not a constant. Means it is dependent on time. If the cause is dependent on time, the effect is also dependent on time. Okay, so that means here we are getting simultaneously the electric field and the magnetic field. So like this, we are getting this electromagnetic wave. So it is a combination of both electric and magnetic fields. See, if you take a DC voltage, there exists the electric field. If you take the DC current, there exists the magnetic field only. Here the electric field only. If you take the AC current as the cause, there exists electric field and the magnetic field simultaneously, and this is called as the EM wave, and it is called as the both simultaneously we are getting. It is an energy format. Here it will be called as it is a power. The electromagnetic wave is the power format. Okay, so like this, how the electric and magnetic fields are generated. Okay. So we got the electric field and magnetic field and electromagnetic fields. Okay, we will talk about the time varying fields next, that is electromagnetic waves. Okay, now first of all we concentrate on the static fields. Okay, so now we got the electric and magnetic fields. Then how these fields can be measured? Okay, how these fields can be measured? It's okay, it can be measured by using the 4 vector quantities. Okay, it can be measured by the 4 vector quantities E, H, B, D. It is a vector quantity, all are the vector quantities. Okay, these are called as the intensity and density vectors. Okay, so this is E is electric field intensity vector. Okay, and it is magnetic field intensity vector. Okay, it is magnetic flux density vector. Okay, here it is electric flux density vector. Okay, so because all are these vectors, see, observe this. What are the units of this? Electric field intensity. Electric field intensity is having the volts per meter. Okay, here it is ampere per meter. Okay, here it is magnetic flux density, flux per area. Okay, the flux per area is Weber per meter square. Okay, what are the units of this? Coulombs per meter square. Okay, these two are the density vectors and these two are the intensity vectors, and these are calculated per unit distance, and these are calculated per unit area. Okay. See, so the measure of field strength at any point can be calculated by using these 4 vectors, and there is a relation between these vectors also. Okay, so this is electric flux density, this is electric field intensity. Okay, so we know these relations, D equals to epsilon E and B is equals to mu H. So that means the measure of field strength is dependent on the what? The mu, and the measure of field strength is dependent on the H also. Okay, so that means the measure of field strength is dependent on medium. The measure of field strength is dependent on the medium. Okay, so if the medium changes, automatically the strengths will be changing. Okay, so these are the 4 vectors we will be using the entire subject. Okay, so 4 vector quantities E, H, B, D. Here one of the important thing is we have to concentrate on the units. Okay, the units are very, very important, and also the comparisons between E and H fields. Okay, at the first one and second one. Okay, these are the 2 important factors we should consider, the units of each and every parameter in this subject, and also while studying the electric and magnetic fields, we have to concentrate on the comparison between the electric fields and magnetic fields, and what are the causes of these electric fields and what are the effects, and what are the causes of this magnetic field and what are the effects. Okay, so it will be for better understanding of the subject, we have to consider these 2 units and the comparisons between the electric fields and the magnetic fields. Okay, so now so what is mu here? What is mu? Mu is nothing but mu and epsilon. Mu and epsilon. What is epsilon? Epsilon is equal to epsilon naught, epsilon r. Here it is the permittivity of the medium. Okay, what is mu? Mu is equals to mu naught, mu r. It is the permeability of the medium. Okay, so what is this epsilon naught? Already we know the epsilon naught is equals to 8.85 into 10 power minus 12 farad per meter, or it can be written as 1 by 36 pi into 10 power 9 farad per meter. So it will be beneficial for you if you remember this. Okay, 1 by 36 pi into 10 power 9 farad per meter. Here it is mu naught is equals to 4 pi into 10 power minus 7 Henry per meter. Okay, Henry per meter. So this is called as the free space permeability. Permittivity, it is called as the free space permeability. Okay, and mu r is equals to 1 for free space. Okay, so the measure of field strength is also dependent on the what? The medium, exactly. Okay, now we got the electric field due to the point charge, and we got the magnetic field due to the current. Okay, so not only this point charge is generating the electric field, but also some other charge distributions are also present which are generating the electric field. Okay, see, if you observe, already we know if you take a point charge here, Okay, if you take the point charge Q, if you take the point charge Q here, it is a point charge. We got the electric field. Okay, we got the electric field. This is the point charge. Next, if this Q amount of charge is distributed along the length of the line, if this Q amount of charge is distributed along the length of the line, then this is called as the line charge. Okay. Okay. So here it is represented with, the point charge is represented with Q. Here the line charge is represented with rho L. Okay. Rho L. This is equals to dq by dl. Okay. What are the units of this? The units of this are coulombs. What are the units of this? It is coulomb per meter. Okay. Now if the same amount of point charge is Q, okay, is spread over a surface, what happens? Spread over the surface, what happens? We will get the, it is called as the sheet charge. It is called as a sheet charge and it is represented with rho s, and sheet charge is equals to, let us suppose the surface area is S. Okay, if it is uniformly distributed, then the rho s is equals to dq by ds. Okay, rho s is equals to dq by ds. What are the units? Coulomb per area, coulomb per meter square are the units. Okay, suppose if you take the same amount of point charge is distributed over the volume. Okay, let us suppose this is the over the volume of V. It is called as, it is volume charge. Suppose if the Q amount of charge is distributed over this volume, this is called as the volume charge. It is represented with rho V. This is equals to dq by dV. Okay. So what are the units? Coulomb per meter cube are the units. So Coulomb per meter cube is the units. See, not only this point charge is generating the electric field, but also the line charge will generate the electric field, and the sheet charge will also generate the electric field, and the volume charge also generate the electric field. So these are called as 1, 2, 3, 4. These 4 are called as the causes of E field. These are the causes of the E field. Similarly, we know that what? Similarly, we know that the current carrying wire, if you come to the magnetic field side, the current carrying wire will generate, what? Will generate the H field. It is I carrying wire. Okay, I carrying wire. Okay, it will generate the magnetic field. We know this. Okay, suppose if I cut this line to a infinitesimally small length. Okay, if I cut this line to infinitesimally small length. Okay. Okay. This will also generate. See, observe this. So this is the I current carrying wire. So not only this I current long length current carrying wire is generating the magnetic field, a small length current carrying wire also will generate the magnetic field. A small length current carrying wire is represented with IDL. Okay, IDL. This where DL tends to 0. Where DL tends to 0 means what? This length is tending to 0. So this length is tending to 0 means we can assume this one as the point. Okay. So not only this current carrying wire, long length current carrying wire generating the magnetic field, but also a small, infinitesimally small length current carrying wire can also generate the magnetic field. So this is causing the magnetic field, this is called as I current carrying wire. I carrying wire. This is called as the point current element. This is called as the point current element. Okay. See, it is the point current element. It is just like a point only. This will also generate the magnetic field. Okay. It is a wire. It is a point current element. Suppose if the same amount of current is flowing within the sheet of length L. If the same amount of current is flowing, I amount of current is flowing. Okay. If I amount of current is flowing like this and it is spread over the length of the sheet. Okay. So if the I amount of current is flowing like this, and it is spread over the length of the sheet, the total I is spread over the length of the sheet, then this is called as the sheet current. Sheet current, and it is represented with K bar. Okay, where K bar is equals to di by dl. Okay, so what are the units of this? The units of this sheet current are the coulomb ampere per meter. So what are the units of this current? The units are amps, amperes. What are the units of this? IDL. Okay, point current element. IDL is current, amperes into meter, ampere meter. Okay, ampere meter are the units of the point current element. Here the sheet current is having the units ampere per meter. Now if the same amount of current is flowing in a solid conductor, okay, if the same amount of current I is flowing in a solid conductor having a cross sectional area S, what happens? Then you will get, then this is called as, it is a solid conductor. It is called as the solid conductor. Okay, and it is represented with Js, current density, J current density J is equals to di by ds, because this I is crossing this surface area, cross section area. So here ampere per meter square are the units. Current per area, it is current density. See, these are the causes of the H fields. So not only this current carrying wire is generating the magnetic field, but also a small length current carrying wire also generating the magnetic field. Okay, this is called as the point current element. The units are ampere meter. Okay, now if the same amount of current is distributed over the length of the sheet, then this is called as the sheet current. The units of the sheet current are ampere per meter. Okay, if the same amount of I is flowing within the solid conductor by crossing the cross sectional area S, then it is represented with the current density. Okay, it is, the units are ampere per meter square. So these are the causes of E fields, and these are called as the causes of H fields. Okay, so these are very, very important. Okay, so depending on these charges of distribution, the effect will also be the orientation of the charges, the orientation of the electric field changes. Here also the depending on the orientation of the charge current, the orientation of the magnetic field is also changes. Okay, now the units are very, very important for each and every parameter. Okay, so here, so in this the very important concept next is the vector calculus, but here we won't teach all the vector calculus and coordinate geometry here. Okay, just we will use some important operators here. Here in the very important operator is the del operator. It is called as the del operator. Okay, del operator. So del operator is nothing but is del is equals to, okay, dou by dou x ax plus dou by dou y ay plus dou by dou z of something into az. Since generally the del operator is a vector operator, it is a vector operator. The del operator is a vector operator. Okay. See why this operator is used. Okay. In the vector calculus, we will be having what? Directional derivatives and directional integration here. Okay, so why we use the directional derivatives? The directional derivatives are used for what? For finding the instantaneous value. Okay, instantaneous value. It is used for finding the total effect in a region. Okay, the directional derivatives are used for the rate of change of a quantity at a particular point at that instant, but the directional derivative integration are used for finding the total effects in the region. Okay, so here we use, in the directional derivatives we use the del operator. Okay, so the del operator is the differential operator. Okay, it is a vector operator. See, this is ax, ay, az are the unit vectors along the x, y and z. Okay, so del of something can be written as dou by dou x of something ax, dou by dou x of something ay, dou by dou z of something az. So it is a vector operator. And this vector operator, suppose if I write any quantity here, okay, so what it is saying? It is the rate of change of that quantity in the direction of x, the rate of change of that quantity in the direction of y, the rate of change of the quantity in the direction of z. Okay, so that means what is this operator? The del operator is used to analyze the, okay, del operator is used to analyze the rate of change of a quantity in the direction of space. In the direction of space, the rate of change of a quantity in the direction of space. Suppose if you take any quantity, either it may be vector quantity or a scalar quantity, how the that quantity is varying in the direction of x, in the direction of y, in the direction of z. Okay, so like this, it is very important operator. Okay, so now what is this vector operator, del operator? Suppose this del operator can be, this del can be operated on a scalar. This del can be operated on a scalar f. Okay, suppose if del is operated on a scalar, then this is called as del f. This del f is represented as gradient. Okay, now suppose if the del operator is operated on the vector, let us suppose some a, okay, this is called as, and on the vector there are two operations here, that is del dot a and del cross A. Suppose, see, the del operator can be operated on a scalar and also a vector. Okay. Suppose if the del operator is operated on the vector in the scalar, then that is called as the gradient. If the del operator is operated on the vector, it is two operations are performed here. Okay. Here del dot A and del cross A. What is del dot A? The del dot A is called as the divergence. It is called as the divergence. What is this? It is called as the curl. It is the divergence of this vector and it is the curl of this vector. Now, this del operator is also operated on what? Itself. Del. Okay. So, what is this? It is also vector, right? Okay. So, here you will get the operation is del dot del. Okay. This is equals to del square and it is called as Laplacian operator. It is called as a Laplacian operator. It is a scalar operator. Okay. It is a Laplacian operator. See, what is the resultant of this gradient? The resultant of this gradient is, again, it is a vector because it is a scalar. Suppose if you write any scalar here, what happens? You will get a vector quantity. It is a vector quantity. So what is this resultant of this divergence? The resultant of this divergence operation. It is a vector quantity. It is a vector quantity. The dot product gives you a scalar. But in general, see, observe this. The divergence of any vector is represented as limit. Mathematically, it can be represented as limit dv tends to 0. dv tends to 0. Closed integral a dot ds divided by delta v. Okay, delta v. Here the curl of the vector is represented as limit delta s tends to 0, closed integral a dot dl divided by delta s, where delta v is the infinitesimally small volume, delta s is the infinitesimally small surface area. Okay, so these are the mathematical representation of this, the divergence and the curl. Okay, so it is a vector quantity. Okay, what about this del dot a? Del dot a, it is a vector. The dot product will give you a scalar quantity. Okay, here what about this? It's a curl. The cross product will give you, it's a vector. So like this. So these are the operations of the del on a scalar and a vector and also on itself. Okay. We will see some important vector identities here. If you write some vector identities, the first vector identity is the curl of gradient is 0. The curl of gradient is 0. Second one is divergence of the curl is 0. These are the two very important vectors. See, it is a scalar quantity. So here you do vector. The curl of this vector is 0. The curl of this is called as the curl of gradient is 0. That means CZ is 0. Okay, the curl of gradient is 0. It is divergence of a curl. The divergence of a curl is 0. Okay, so dc is 0. You remember this. Okay, divergence of a curl is 0. And the third one is del cross A is equals to del of del dot A minus del square A is one more important, the vector identity, and which will be used in the solving of the problems. Okay, so now come to the next topic. What is the divergence? Already we observed the divergence. The divergence is del dot any vector. Okay, what is the divergence means? The divergence is nothing but the outflow of the flux, the outflow of the field, the outflow of the flux from an infinitesimally small volume. So this is called as the divergence of any vector. So that's why we have written, okay, what is that? Outflow of flux from the any infinitesimally small volume. So that's why I have written delta V. Okay, the delta V tends to 0 means the infinitesimally small volume. So what we will see, what is the numerator term, integral A dot ds. Okay, so what is meant by this outflow? Now the outflow from infinitesimally small volume. Okay, so what is meant by outflow? Suppose if you consider any point charge Q here, okay, the effect will be outward from this, the effect will be outward from the charge, we know this. So the electric field will be radially outward from the charge. Okay, if you take a point charge here, the electric field will be radially outward from the charge. Now if you consider at a distance here, you can assume a sphere like this. You can assume a sphere around this at a distance of some r1. Okay, so on this, what we can say, the strength of this field will be, the strength of the field on this sphere will be same. Let us suppose this is x, because this point, this sphere is, if you construct a sphere around this point charge, this on this sphere, the strength of the electric field, the strength of this electric flux will be same on this sphere, because these all points are equidistant from the charge. Suppose if you consider this surface area, what happens? So on this line, on this surface, you can say some strength y, and this y will be constant on this surface. Okay, because these all points are equidistant from the charge. Suppose if you consider one more surface around this point charge, let us suppose the strength on this surface is z, but as the common sense saying, that is what, the strength here is greater than this one and this will be greater than this one, because it is nearer to this. Because of this point charge, the strength will be more here, because it is nearer to this. Here automatically the strength will be reduced, here automatically the strength will be reduced. So we can say that the strength x must be greater than z. Okay, but if you observe, see what is the outflow? The outflow is nothing but the outflow of this flux. Okay, the quantity of the flux crossing this surface area. Okay, so if you observe this, for simple understanding I am saying this, observe this, the number of flux lines crossing this, okay, the number of flux lines crossing this surface area is also leaving this surface area, that means the quantity of the flux crossing this surface area and this surface area and this surface area are same, means, understand? So that means the outflow is constant. What is called as? The outflow is constant. Okay, and this outflow is, suppose see, if you put a more amount of charge here, you will get more amount of outflow. If you put less amount of charge here, you will get less amount of charge. So that means the outflow is dependent on the cause, and this outflow is constant and it is proportional to the central cause. Okay, so what's happening here? The strength here will be more, here the strength will be less when compared to this, and here the strength will be less when compared to this. The strengths are reducing as the area of this, surface area is more, but the total net flux coming out of the surface is constant. The outflow is defined as, the outflow is equals to the strength into the area. The strength into area. The strength into area is a constant and it is proportional to the cause. What is the cause? We will see. Okay. See, it is a constant. What is the cause here? It is cos Q. Now, what is the strength? See what happens here? It must be constant. The total outflow must be constant. The total outflow must be constant in all these three surface areas. Okay. See what's happening here? But the strength is decreasing as we move away from the charge. That means if you increase the surface area, automatically the strength will be decreasing. So that means as the area increasing, the strength of the field also, the field will be decreasing. But what is the strength here? The strength is equals to, what is this? The constant per area. The constant per area. So it is equals to, if the proportional constant is 1, what is this one? This is the cos per area. What is the cos? The cos is Q. Area is, what are the units of this cos? Coulombs per meter square. The units are the coulomb per meter square. Okay, the coulomb per meter square. So what are the, so the coulomb per meter square are the units of what? The electric flux density D. So here we can call this strength as D now. Okay, so here we will be having some D1, here we will be having some D2, here it will be having some D3. Okay, the strength on this surface will be D1, the strength on this surface will be D2, the strength on this surface will be D3. Here D1 is greater than D2, greater than D3. So it is just common sense that if you move away from the charge, automatically the strength will be decreasing because the area of expansion is increasing. Okay, so this is the strength. Okay, now I define the outflow. The total outflow within the closed surface. Okay, you take the total outflow within the closed surface is equals to the total outflow from this closed surface is equals to what? I take this closed surface integral. Okay, what is the strength? Strength into area. I am taking this integral. Okay, the strength into area is equals to constant. Okay, and this constant is proportional to the central cos, and this This constant is proportional to the central cause. What is this? This constant, I am saying that this is what? The total outflow within the closed surface. I am naming this one as psi E electric flux. The total outflow of the flux. Okay? It is called as the electric flux. It is proportional to what? What is the cause? Q. Right? So from this we can write, if the proportionality constant is 1, the closed integral d dot ds is equals to a q. It is equals to, also called as psi e total. It is called as the psi e total. Okay. So this is called as the Gauss law. This is called as the Gauss law. Okay. So what is this? The Coulomb per meter square into meter square. The units of this one are Coulomb per meter square and ds is meter square. Get cancelled. You will get what? The coulombs. Okay. The total flux coming from this surface is equals to the total charge enclosed in the volume. Okay. What is this? Q. It is the charge enclosed in the volume. This is the Gauss law. What is the Gauss law? Is stating that is the net flux leaving any closed surface. The closed surface is equal to the charge enclosed in the volume. Okay, the charge enclosed in the volume. So how much amount of charge is put in this volume is equal to the net outflow from the net flux leaving the surface. Suppose if you put one more Q1 charge is placed here, then this will be equals to plus Q1, like this. Okay. So this is the Gauss law. This is called as the Gauss law. Now what is the divergence now? This is already we know that it is what? Closed integral d dot ds is called as the total outflow. The net flux leaving any closed surface is called as the outflow. Okay. The outflow within the closed surface. So now what is the divergence now? The divergence is called as what? What is the divergence? The divergence is represented with del dot. See, what is the divergence? Divergence is equals to what? Closed integral, already we know, d dot ds divided by what? Delta v, where limit delta v tends to 0. Okay, this is called as the divergence. So this is equals to what? The divergence of this vector d. Okay, the divergence of this vector d. So this is the divergence. What is this divergence? The total outflow from any infinitesimally closed volume. Okay, so that means, so this is del dot d. So what is this del dot d? This del dot d is equals to what? What is this? D dot ds. D dot ds is equals to q divided by volume. The q per volume is nothing but the charge per volume. It is called as the volume charge density. It is represented with rho v. It is represented with rho v. It is called as the volume charge density. It is volume charge density. What are the units of this? What are the units of this? Already we seen Coulomb per meter cube. Okay. So what are the units of this? What are the units of this? Coulomb per meter square. And what should be the units of this? What should be the units of this del operator? The units of this del operator must be per 1 per meter. 1 per meter. 1 by meter. Okay. So del operator will be having the units of what? Meter inverse or 1 per meter. Okay. Because what is del operator? Dou by dou x, dou by dou y, dou by dou z. Okay. So in the denominator there are the lengths. So that's why the units of the del operator are what? Meter inverse. Okay. And this is called as del dot d is equals to rho v. Okay. It is also very important relation, and this is called as the Gauss Law in point form or derivative form. It is the Gauss Law in the derivative form or the point form. It is the Gauss Law in integral form. It is the Gauss Law in the integral form. Okay. So what is the Gauss Law is saying? The total flux coming out of any enclosing surface is equal to the, suppose if you take any enclosing surface like this. Okay. Suppose if this enclosing surface is having a point charge q plus q1 and q3 and q6 like this, minus q3 minus q4 like this. Okay. Now what is the total flux? What is the net flux leaving this closed surface? The net flux leaving this closed surface is equal to the charge enclosed in this closed surface. Okay. The charge enclosed in this closed surface. So that means what is the net flux? The net flux is equals to q plus q1 plus q3 plus q6 minus q4. Okay. So like this we have to calculate the total flux coming out of any closed surface. Okay. So now, so this is called as the point form of the Gauss Law, and this also gives you the strength at the cause. It also gives you the strength at the cause. Here what is D? Here D is nothing but, here D is the strength around the cause. Already we know what is the D, D1, D2, D3, or they are the strengths around the cause. But here if you take the divergence of this, we will get the strength at the cause. Okay, the strength at the cause is equal to the rho v. Okay, so this is the divergence of the electric flux. Here the divergence of the electric flux density. Similarly, come to the magnetic fields. We found that what? Closed integral d dot ds is equals to q. Okay, and what is the differentiation form? Differential form, del dot d is equals to rho v. Similarly, what is the curl? The curl is equal to the circulation of the field from any infinitesimally small surface, infinitesimally small surface area. Okay, so how this is mathematically represented as what? Del cross A is equals to open closed line integral of A dot dl divided by the delta S. Okay. So this is called as the circulation. Now what is meant by this circulation? Circulation of the field, the circulation of the flux, field or flux. Okay. Suppose if you take any current carrying wire like this, I am placing the current carrying wire like this. You know the magnetic field will be around this. Okay. Already you know that the magnetic flux lines are circles. The magnetic flux lines are circles. Okay. Magnetic flux lines are circles. If you observe this, see, this is a circular line, it is a circular line, these are the lines, these are the magnetic flux lines. Okay. So due to this, you will be having a field strength here, here and here. So if you consider this circular loop, you will be having the same strength because all these points are equidistant from this cause. If you find the strength on this line, you will be having the same strength because these all points are equidistant from the cause. Here also same. So let us suppose this is x, y and z same. We know that x is greater than y is greater than z, because here it will be having the strength x is greater than this and it is greater than this. Okay. Now, but even though the strengths are varying, the total flux circulated on this line, the total flux circulated on this line, the total flux circulated on this line must be constant. That is what Amperes said. Okay, what the Amperes has said, that is the circulation, similar to the previous case, the circulation of the flux is equals to same, the strength into the length must be a constant and it is proportional to the cause, and this constant must be proportional to the cause, and he defined like that. What Amperes as did means, even though there is the increment in the length as we move away from the cause, automatically the strength will be decreasing. Okay, but the total flux circulated on this line, the total flux circulated due to this current on this line must be constant in all the circles. Okay, that's what he said. So it is the strength into the length. As the length, what is the length? This length means, what is this length? Length is equals to 2 pi r distance. Let us suppose the radius of this line is, of this circle is r, then the length will be 2 pi r. So on this 2 pi r length, the same strength will be x. Okay. So the total outflow, the total circulation on this length, the total circulation on this length, the total circulation on this length, the total circulation of the field on this length is constant. Okay, the circulation is nothing but the strength into length. As the length is increasing, what happens? The strength will be decreasing. But one is increasing, one is decreasing means you are getting a constant. Okay, and this constant must be proportional to the cause. What is this cause here? Current I. The cause is current I. So now the strength into length. See, on the closed surface, the circulation of the field, the circulation of the flux, what kind of flux? It is a magnetic flux, is equals to, on the, suppose if you take any closed surface, okay, if you take any closed length, the circulation of the length. So first of all, we will see what is the strength here. What is the strength? Here the strength is equals to what? Constant divided by the length. What is the constant? At a cos, if the proportionality constant, cos divided by the length. What is the cos here? Current divided by length. means ampere per meter. The ampere per meter are the units for the term H, the magnetic field intensity. So we can say that this is what the strength term here, it is the magnetic field intensity H. Okay, so this is the strength. Now we can write that what is the circulation. The circulation can be written as the circulation of flux is equals to what? The closed, within the closed length, the strength. What is the strength here? The strength is H. The strength into length is equals to the constant, and this constant is proportional to the central cos. What is that central cos? I. Okay, and this constant is proportional to the central cos. If the proportionality constant is 1, we can write that H dot dl is equals to the current. This is called as Amperes Law. This is called as the Amperes Law. Okay, so now what is the Amperes Law is saying? The Amperes Law states that the circulation, it is the statement of the Amperes Law, the circulation of magnetic flux through any closed length is equal to the current crossing the surface. Okay, current crossing the surface. What is the meaning of this statement is the circulation of magnetic field on any closed length is equal to the current crossing the surface. See, take this closed length. Okay, the circulation of magnetic flux on this closed length is equal to the current crossing this surface. This entire portion is the surface. The current crossing this surface. What is the current crossing the surface? I. Okay, suppose if you put one more I1 here, the current crossing this surface will be I plus I1. Suppose if you put minus I2 here, okay, you will get I1, I plus I1 minus I2, like this. So the circulation on any closed length is equal to the current crossing this surface. What is the current coming out of this? The current coming out of the surface is I plus I1 minus I2. So like this. See, because this I is only the cos, we have to write this I. So this is what? The Amperes Law. Okay. So now, so what is H here? H is the strength around the cos. Here H is nothing but the strength around the cos. That means, let us suppose this is H1, H2, H3. The H1 is same everywhere, H2 is same everywhere, H2 is same everywhere on this line. So here H1 is greater than, H2 is greater than H3. Like this. So now, what is meant by curl? The curl is equals to, what is the curl? The curl of any vector is equals to curl of any vector H can be equals to what? The curl can be written as what? Now we are defining the curl. Already we defined the curl as closed line integral of H dot dl. I am writing the curl of this one. Okay. The total circulation from any infinitesimally small surface area. The total circulation is this one divided by any infinitesimally surface area. Delta S tends to 0. Okay. Is called as the curl of this vector field H. Okay, the curl of this vector field H. See, what is this? This is what actually the total circulation. The total circulation coming out of this surface is nothing but the current. The current per area is nothing but what? The current density. Or otherwise, you can also write like this. What are the units of this? Ampere per meter. What are the units of this? 1 per meter. So it will be ampere per meter square, or the units of the current density. So this is called as the curl of the magnetic field intensity. This is also called as the strength at the cause. It is the strength on this H. Okay, strength on this at the cause, the strength at the current carrying wire. Okay, so if you come out of this, what will be the del cross H? Okay, we will see in the next class. Okay, so this is called as the curl and divergence of the electric field intensity and magnetic field intensity. Okay, till now we defined the curl of magnetic field intensity and the curl of electric field intensity. The curl of the magnetic field intensity and the divergence of the magnetic field intensities. Okay, till now we discussed how the electric field is generated and how the magnetic field is generated. So what are the causes of the electric fields? What are the causes of the magnetic fields? What are not only the point charge and not only current carrying wire, what are the remaining causes of the electric and magnetic fields? And after that, we taught the vector operator called the del operator, and which is very, very important, and it is useful for the solving very good problems. Okay, so here del dot and del cross we calculated here. What is del dot? It is the divergence. What is the del cross? It is the curl. Till now we calculated the divergence of the electric field and then the curl of the magnetic field. Okay, so here the strength at the cause, there also we find the strength at the cause. The strength at the cause in the electric field is del dot D is equals to rho V. The strength at the cause in the magnetic field is del cross H equals to J. Okay,